All right, hello class, welcome back to part B of this lecture 6. In this part of the lecture we will briefly, I like to think, go over concepts of observers. So this is something that is a little bit more complicated than the controller case. So remember, in the previous lecture, lecture 5, we defined the problem of feedback control. We motivated the problem of feedback control as we wanted to measure all our states, full state feedback control, full state, static, important, full state feedback control, feedback. And for that, we needed measurements of all of the states, right? Because it's full state, right? But as I argued previously, these states are somewhat artificial, right? They're an artifact of how we represent the dynamical system that we're trying to control. So the things that we really measure are y of t. Those are the outputs, the measured outputs of the system. We haven't done optimal control, so we don't have regulated outputs. We only have measured outputs at this point. Right? And presumably there's some relationship between the states and the outputs, right? But there's most likely fewer outputs that we measure and with respect to the number of states. So we've defined our controller in terms of these sort of like somewhat arbitrary choices of state. And what we really have available are the measurements, right? And so the question is, how are we going to implement this controller? So question of implementation. Question mark. Right? And so, of course, what we want to be able to do is, even if these states are somewhat artificially designed, we want to be able to observe what we can actually observe, and then be able to infer what the state should be to give us that particular output. Now, obviously, C is not invertible, right? So we can't just do it direct. Can't just invert C. It's usually skinny, right? That's when we mean fewer measurements than we have states. So how are we going to accomplish this? Right? Well, that's where we get to this. That's where we leverage this idea of observability. Right? We talked about inversion of the map or this function from state to output. But in order to do that, we required measurements of that output over some non-zero time interval. We weren't talking about measurement mapping instantaneous states to from the output. We're talking about observing y on some interval and then using that sort of function to infer what the initial condition was initially. Right? So we could apply that, right? We could, observe the output on a sort of a very small time interval, and then say, hey, that's our current state. But that's not right? There's a delay in there, and furthermore, right, how we defined observability was a little bit, mathematical, a little bit theoretical, right? We have this absolute measurement of the functions going on in time. And we take that function, and then we're going to somehow invert that function to get the initial condition, right? That's not really satisfactory, I guess you'd say. What we want to be able to do is do this in real time. We want to be able to have an estimate of the state in real time, which we can then implement using this controller, right? So we can use this real-time estimate to update our control effort in real time. And so that problem is a little bit different than the observability, but we'll see that essentially the existence of an observer which does this is equivalent to the question of observability. So all of the stuff we went over in part A will not have been in vain. So let's sort of map out what the goal here is then, right? So we want to, so we've got our input, right? U of t, maybe. We have our system, produces an output, and we have those output measurements. So we'll branch them off, bring them down here. And so we have those measurements of the output, and we'll put them in an observer block. And we want the output of our observer block to be x of t. Well, we can't do that exactly, so we'll make that instead of x of t an estimate of the actual state. And so what we'd like is if there's an actual state, which through some fictitious output here, we'd like the difference between those two things, right? We'll put a negative sign here. That error, we would like that error to go to 0. Right. So this is that's sort of our block diagram output. We can do a little bit more. We can say, well, we should know what the input is because we created it. So we can also say this, right? We can give our observer a little bit more information, so we can give it u of t as well. And then, of course, don't forget, right? We eventually closing the loop on this thing. So when we implement our controller, obviously we can't measure x of t as we argued. So we'll, of course, use the estimate of the state, and then we'll put that as our input and close the loop on the system, right? And in this case, we would like the system to be stable, right, in closed loop, right? So we have two goals, right? Basically, one is design an observer so that this error goes to 0, and then when we implement that observer, we would like the state itself in closed loop to go to 0 as well, right? So that's sort of twin goals here, and we'll see that they're not mutually exclusive. So let's concentrate then on this block, the observer block. Well, what is that? Well, as we argued, we've got this observer block. It's a system, right? In that it has two inputs, u of t and y of t. U of t, of course, we know because it's actually depends on the output of the system itself. This system here, this observer system, right? And so we want the output of that to be x hat of t, and we want the inputs here to be u of t, and of course we need measurements, right, from the output of the system itself, right? So what's inside that block? Well, we can't make it a static function, right? So we'll start with that. There's no static observer design. That would be static output feedback, which is unsolvable. Well, we believe it's insolvable. Feedback. Question mark. And I'll just put a little box around that and say unsolvable. And that would be the case where we have these measurements, right, y, and we want our u of t to be a static function of those measurements. Right? That problem is unsolvable, so we have to put some dynamics inside of our observer in order to make this problem tractable. Right. So what kind of dynamics are we going to put in there? Sorry, forgot to turn off the air conditioner. So we assume, of course, right, if it has dynamics, we assume those dynamics are going to be linear, and we'll assume that they have some state space representation with like 4 matrices, A, B, C, and D. Now these A, B, C, and Ds, on the next slide we'll show, are not necessarily the same dynamics of the system itself, so that's not really our observer. Right. So what are the dynamics then? So we'll try and make it general, as I argued, right? We have 2 inputs to this system, right? We have the measurements, y of t, and of course we know what our u of t is, so we can have that as an input as well. And the output should be something. In this case, we're going to call it x hat t, the estimate of the state, hat for the estimate. So what's the sort of most general form of linear systems that we can construct given these inputs and this finite dimensional outputs? Well, we'll just parameterize it with 6 matrices. If you want, you can write the 6 matrix representation. So we haven't talked about the matrix representations yet. But, so we've got M here, and it's got 2 inputs and a single output. So there's this is input is y, t, u of t, and there's a p there and there, and then our outputs q, r, and s. So that's how we write system state space representations, just by decomposing the inputs to the outputs. Right? So z dot equals, and then here we have x hat equals, right? And of course, we don't know what our initial conditions to the system or to the observer are. We run it all the time, so right, the actual initial states don't really matter because right, there's they evolved from some infinite time in the past. So we'll just generally like this to like work for any initial conditions. And of course, we want it to work for well, in closed loop, but we'll just say for any inputs, signals. So we would like this thing to go to x of t. We would like those to be approximately the same. And so if we define our error dynamics, E of t here, right, as the difference between these 2 states, or the estimate of the state. And actually, we usually go the other way around. So we subtract the state from the estimate, so that if our estimate is high, then our error is positive, and our estimate is low, our error is negative. Right? So how do we choose then these, 6 matrices, right? We got a lot of flexibility, 6 parameters. How do we choose those 6 parameters based on our notions of observability that we talked about previously? So first of all, we're going to constrain ourselves to state spaces where that z dot, right, I forget, I think it was m z of t, right? So basically z of t is in the same dimension as the state itself, right, which is relatively reasonable. We'll show, as we argued, right, if the problem is if you make the state of, have 0 dimension of the observer, well, then you're back to the static case, and so we know that's not solvable. And it turns out if you make it too big, then, well, you can make it too big, but you don't need all that dimensionality. So we can assume basically that the dimension of the observer is Rn, the same dimension as the state as well. And anything less than Rn is just an NP hard problem. So it's generally a hard problem. So it's not tractable problem. So we'll assume it has the same dimension. So, okay, well, here's our system. And here's our observer. And remember that sort of block diagram that we had there with the output, y, going to our observer. And here's our input. and the output from the, well, we know what the input is, and the output for the observer actually is the input to the system. So they're interconnected in that way. And here we'll put a little block between the two, K, a static gain block, and those are, we don't have a 0 there, so we'll do that. And so we want the system in closed loop then for the actual state to converge to our estimate. And here we will have a negative sign. So that's x of t, and there's our estimate of the state, x hat of t. And that's our error. We want this error to go to 0, right? That's our goal. So if we want our error to go to 0, well, it stands to reason that we should write out what the error dynamics are. Now again, I apologize because this slide is really overly complicated, because in like 2 slides from now, we'll reduce it and show we don't need all this complexity. But for now, we'll leave it alone, because ultimately when we do optimal control, this complexity will be useful. If we just want it to go to the error to go to 0, we don't really need all this complexity. But in the most general case, we sort of do. So we'll write it down, but keep in mind that there's a lot of things here, a lot of terms, which we're not going to need. So let's write it down anyway. So here are the error dynamics. Well, it's the dynamics of the error, or the derivative of the error is the derivative of the state. And again, actually, technically, we should swap those, but we haven't done that here. So we'll ignore that. So we just plug in then, right, for the x dot here, and we get these terms here. And we plug in for the x hat dot right here. And, well, those terms go there, that term goes there, and that term goes there. Right, so then what happens? Well, z dot, we know what the expression for z dot is, right? That goes to this term right here, this big term right here. Y dot, right, well, you just differentiate this, and that goes to this term right here. And then u dot, well, u dot is just u dot. Well, can we simplify anything more? Well, yes, it turns out we can simplify a little bit more, because we do still have that expression for x dot, and we can plug in ax plus bu here. Where does that go? R, here it goes. Right? And that x dot goes down there. Right? And so now we're just grouping terms together. Here we could group all the terms that multiply u dot, so we group those two together. We simplify these out. All the terms which multiply z show up there. And then we group the terms which have the error in them. And so that's terms which naturally have right, this difference here. And so those all go into here. And then we have the leftover terms which multiply z. We have the terms which multiply y. We have the terms which multiply u, and the terms which multiply u dot. Right. So again, relatively complicated, right? Not as simple as we'd like. It's unclear, what conditions we can impose on these dynamics, which will cause E dot to be stable. Well, one condition, right, that we could obviously impose, right, is that just like everything here is 0, and this is 0, 0, 0. We could just make all that 0, and then if we have E dot equals some matrix times E, call it A hat if we like. If this is Hurwitz, well, then we're stable. Right. And actually, it turns out, well, that's what we'll do in the end. We're going to make all these extra terms, disappear. But we'll do that on the next slide. I'm not going to do it on this slide. So to get away from the complexity, again, we choose a very particular form of observer, right? It has a name, Luenberger observer, right? For David Luenberger, Dave. And why did he get his name on this observer? Probably because he proved most of these properties. I don't actually recall. I actually took a class from David Luenberger back when I was at Stanford, back when he was around and kicking. But not on this subject. It's very complicated. Optimization by vector space methods was the name of the course and the name of his book, because that's the book he used to teach the course. A very nice book, but not really appropriate for this class. In any case, he chooses this particular form of observer where the dynamics are rather simplified. So this is our observer. Okay, so first of all, he gets rid of all the messiness with the output, right? So he makes the state itself the estimate, right? So this is the observer state. And so there's no difference actually in this class of observers between the observer state and the estimate of the state itself, right? They're the same thing, right? So no gets rid of those three parameters right off the bat. So in this case, right, this parameter is 0, this parameter is 0, and this Q is just the identity matrix. So that those three extra parameters don't really factor in. So what does the rest of the observer look like? So it's based sort of on what you would like an observer to do, sort of an intuitive understanding of what's going on. So it has this form, right? A plus LC Z plus, so this is M, this is N, and this is P, right? So he chooses these particular values of M, N, and P, where actually the only unknown is C. The D, the B, the A, those all follow from the system itself, right? Remember the system x dot equals A, x plus B, U, and the output of that system was y equals cx plus du. Right, so these four parameters are given, right? There's no flexibility. Oh, sorry, not C, my bad. The unknown is L, and so that's the observer gain. So that's similar to, remember now we're getting closer to the feedback control problem where the only parameter we had to choose in that case was K. Control gains. And in this case, L is the observer gains. Well, why do we call it gains? Well, just a second, I'll get to that. Right. So basically, what does this observer look like? Right. So this is our estimate of the state, right? And so the idea is that the state should approximately have the same dynamics as the system itself. So if you have a state, or an estimate of the state, it should approximately evolve along the same set of dynamics as the system itself. Right? And so that's this term here, z dot equals az plus bu. So that's update of your estimate of the state. Right? And then, in addition to that, we have a correction term. And obviously, if there was no correction term, your estimate of the state, even if you're propagating it with the same dynamics, is going to diverge from the state, right? So we had, here's the actual state, and it's evolving like that. Even if, if our estimate was off by a little bit, it might follow state for a while, but then it would eventually diverge, and this error would get large. And so that's so the propagation of the state is the first step. But then in addition to that, we have a correction step. So at every time step, we're continuously updating or correcting errors in the state. And so that language correcting based on errors, right, is sort of indicative in that, right, this whole term here, right, is the error. Well, we can't actually measure the error in the state, right? So that's not an option. But we can measure the difference between what we predict the output. So we can only measure outputs, right? So what error do we have available to us? Well, we have, in the terms of errors, are errors in the outputs, or the predicted output. Right, so remember, we can measure in real time the actual output. Right, and here it is, actual output. And based on our estimate of the state, we can predict what, if we were correct as to what the actual state is, what output it would produce. Right, so that's the sort of y hat, if you like, y hat of t. And again, just based on our model of how this actual state influences the actual output, right? And of course, in real systems, we'd have measurement noise and all that, but we're ignoring that for the moment. Right. So we have this error in our predicted output, and then we want to somehow update or correct our estimate of the state. We want to evolve it, push it in the right direction based on that predicted error, or the error in the predicted output. And so how do we update our dynamics based on that? That's where this observer gain terms come in, right? So this is the observer gain times, if you like, y hat of t minus y of t. And here we've put it actually in the correct order, right? So we have y hat minus y. So this is our predicted output, and this is the actual output. And then those get mapped through a set of gains, or multiplication factor, to the dynamics of the estimate as well, which is being constantly updated according to our model of how the states evolve as well. Right? So if you know about Kalman filters in a way, this is the same thing, the same idea. Kalman filter is just sort of an optimal, in some sense, version of this Luenberger observer. Okay. So now we've taken those initial 6 parameters in our observer, and we've gotten rid of almost all of our flexibility except for this this observer gain, which we have yet to determine how to choose. Right. So if you plug these numbers in, M, N, P, Q, R, S, into the dynamics for the observer we had on the previous slide, right, then what you find, right, is that these most of these terms simplify. So particularly all those other terms that we wanted to get rid of are all become 0. So this was the one I think with the this is y dot, and I had u dot here, and this was u. So they all go to 0. Wait, there's another one here. So there was u dot, u, y, and y, and z, right? Z was the third term there. And I think I got those backwards. Right? So u dot, u, and y, right? So all those terms go to 0. And the only one left over is the term which multiplies the e of t. So e dot of t is this big matrix here times e of t. And that big matrix itself becomes rather simple. It just turns into a plus lc. Okay. So these terms this term goes away. This term just becomes m. Actually, it should be an m. And then it simplifies to a plus lc. So then the closed loop dynamics of the error system, right, the error dynamics, simplify actually to something which is much, not only smaller, but very close to what we had in the controllability case. Remember, we were designing u equals kx. We found that the closed loop dynamics were x dot equals a plus bk x of t, and we wanted to, right, make that system Hurwitz. A plus bk Hurwitz. Choose k such that that A plus bk was Hurwitz. In this case, we want to choose L so that A plus LC is Hurwitz in this case. So there's very similar concept, of course. The only difference really is that, of course, we're using a parameter C as opposed to B, but that makes very little difference. So from the problem optimization perspective, the only real difference is that L is on the other side of the matrix C, whereas here K was on the right, L is now on the left. The difference there actually, from a pure optimization standpoint, is actually helpful in that we don't need a duality transformation when we're doing observer design. So it's on the left. And so to do our variable substitution, in this case, we don't need duality. But in fact, of course, what we do is we do use duality in order to just transform this problem to the controller synthesis one, which we've already solved in the previous lecture. So specifically, right, remember our goal here, right? We have a system. We have an output from the system going to an observer. We have the actual state of the system. We have the estimate of the state from the observer. And we want that error to go to 0. Right? So for any initial condition, basically. So in a way, right, this is very similar to the controller synthesis problem, right? And in fact, right, we can just apply the result that we had for the controller synthesis case to the observer synthesis case by considering controllability of the dual problem, right? Considering controllability of A plus LC transpose, which is, of course, A transpose plus C transpose L transpose, right? And now here we have the uncertainty, the variable on the right. Right. So this is our new B, this is our new A, and so we just have this the controller synthesis case. Right. So we can then rely on all those big powerful results we had for controller synthesis to say that not only is the system stabilizable, can we design a stable observer if and only if the system is observable, but we can go further and we can say that the eigenvalues of this closed loop aerodynamics are freely assignable. We can assign them to any particular choice of eigenvalues if and only if the system is observable, just by leveraging our controllability result. Okay. And we haven't talked about detectability very much, but we'll, yeah. So, and this, and it turns out, right, that this result applies not just for our particular choice of observer design, but actually applies to any observer design, right? So, even if we have 6 parameters, the 6-parameter case, this result still holds necessary and sufficient. Right? And that's not surprisable, right? Because if it holds for a special case of the 6-parameter case, the 1-parameter case in the Luenberger observer, obviously it holds for the 6-parameter case as well. Right? And so what this shows is that you don't need all those parameters, right? You don't need like 6 parameters. 1 parameter is necessary and sufficient for design of stable observers. And furthermore, you can, for observers where the eigenvalues, the dynamics are assignable. Now, this doesn't hold for optimal observers, however. So not true for optimality. And so we'll come back to that when we talk about optimal control. Right. But again, it's a very powerful result, and it says that we can reduce our observer design problem to essentially a controllability feedback gain problem. Right? And so now, of course, because we solved this this feedback gain problem using an LMI for controllability, we can also extend those results in a straightforward manner without any additional theorems or proofs to observability as well. Right? So, for example, the LMI for stabilizability carries over directly to an LMI for observability. Right. And we can see that, right, just by saying that, you know, the eigenvalues of A and A plus LC are equal to the eigenvalues of A plus LC transpose. So take a transpose of a matrix, the eigenvalues don't change. And so we can find a K such that A transpose C transpose, right, is stable for the controllability case. We can use that result to design an observer as well. Right. So if we solve this LMI, right, then that says that. So if we solve this LMI, that says that A transpose plus C transpose plus BK, or I mean A plus BK, C transpose. Let's call this, for the sake of brevity, K. So it says that these eigenvalues are all negative, and the controller which gives you that is K equals ZP inverse, remember. But of course, we're looking for L transpose in this case, L transpose. And so we want L transpose equal to that. And so we get, to get our L transpose, we just take the transpose of K. And so that just becomes P inverse Z transpose, right? And that's our observer gain. Okay. So now we, in a relatively straightforward manner, went from our LMI for stabilizability to an LMI for observability. And furthermore, we used that LMI to get the gains for our Luenberger observer, which guarantees that the error in our system will go to 0, and it will do so as fast as we like through the eigenvalue assignment problem. Now, okay, so we've got an LMI which will guarantee that the states without an observer go to 0 as fast as we like, and we have an LMI which guarantees that the error in our estimate will go to 0 as fast as we like. And so then the next step then is to combine these systems, close the loop on this sort of outline. So that if we take our X hat here and we plug it into that K to show that this closed loop system, right, then this, this actual state will go to 0, right? So taking our observer, constructing an estimate of the state, using feedback on that estimate, and we want to show you that using that estimate, that structure for the controller, observer-based control, enforces the stability of the closed-loop system. So one way to do this sort of heuristically, right, is to just make sure that your estimate of the state goes to 0 the error in that estimate goes to 0 very fast, and then just intuitively, if there's not much error in the estimate, then there shouldn't be much error in your implementation of the controller. Right? But that's sort of like a hand-wavy thing to do. But it's generally how people design these things. They generally make these, the eigenvalues of A plus LC, we want to make them generally more negative by an order of magnitude than the controller eigenvalues. So order of magnitude more negative. Than those of A plus B, say A plus BK. Technically, we don't need that for stability in closed loop, as we'll see on the previous slide. So this is the implementation of that block diagram which I talked about. Right. So this is the implementation right here. So here's our system. Like this thing right here. Its U is given by a gain times the estimated state. The estimated state is has a set of dynamics, right, given by what's inside the observer. So that's that block right there. And what we want to say is that if we can now construct the initial condition to state map, so x naught, x hat naught, to x of t and e of t, right? That closed loop system is stable. So if we look at the overall, so close the loop on all these inner blocks. When we close that loop, this map is stable, right? And that's what we want to ensure here. And what we find out is that it is, right? So basically what we show is that the eigenvalues of this larger block here are actually nothing more or the same as the sum of the eigenvalues of A plus LC plus the sum of the eigenvalues of A plus BK. So technically, we don't really need these eigenvalues to converge faster than these, but that's generally how people design these things. So, again, saying nothing about optimality or anything like that, but that's what we're looking at. And so the proof of this is relatively straightforward, and it's so classical. I'll just prove it real quickly. So, right, we just write down the dynamics. Here are the dynamics of x dot. They are coupled, right, with this estimate of the state. And, I should just mention, like, why are we proving this, right? I mean, it may seem obvious. Well, if x is converging to x, and if I used my x as x hat, right, it was stable. So through some hand-wavy argument, you could sort of argue that this is going to be true, but that's not a proof, right? There are ways that things could go wrong, right? Even though your error is converging to zero, that error may excite the states of the actual system in some special way, which excites a mode of your, or some hand. There could be some counter argument, right? But what this shows that the counter argument doesn't. Well, this is a proof, right? It proves that the closed loop system is in fact stable, right? And it's not entirely obvious, right? So if we construct the dynamics, right, here's the dynamics of x dot. So we have those here, right? So we have this aggregate state, which is the combination of the state of the system and the state of the observer. So we pile those states together, get an aggregate state. We write down to the dynamics. Well, these dynamics come down to the first row here. X dot equals AX plus BK x hat. And the dynamics of the estimator, right, given here. Well, actually, we wrote those out on a previous line, so we could just skip to that line right there. So if we write those out in sort of the state space matrix form, we have x hat dot equals, so simplify that a little bit. So we isolate terms which multiply x and x hat. Minus LC, right, comes down there, times x, and a plus LC plus BK comes down here. And those multiply x hat. So you can sort of see that it's not entirely obvious that this system would be stable if just the eigenvalues of a plus LC and the eigenvalues of a are negative. Right? So it's not entirely obvious that this is stable, just based on individual stability of a plus BK and a plus LC, because the BKs and the LCs get shifted around quite a bit. But we'll see, in fact, that it actually works out. In fact, actually, you don't really need this the proof, right? If actually you constructed your aggregate state in a different way, if you constructed your aggregate state like this, x of t and e of t, it would actually work out quite simply. But that's not obvious that you'd want to do that. So here's our state space representation of those initial aggregate dynamics. And we want to study the eigenvalues of this big matrix. Right. And how do we do that? Well, it's not obvious what they are at this point, but what we'll do is we'll apply this unit similarity transformation. So the eigenvalues of the matrix don't change under a similarity transformation. So similarity transformation is just an invertible matrix, right? And so we choose this for our similarity transformation. It's invertible, obviously, because we have subdiagonal terms which are both full rank, and there's 0 up here. And then whatever this is, it doesn't matter what that would be. If these two are invertible and this is 0, then this is going to be invertible as well. But it's chosen in such a clever way that its inverse is actually equal to itself. So that's a nice little feature. It actually corresponds to changing the states to x and e of t. So, but that's just, you didn't know that a priori, so forget I told you that. So do the similarity transformation, construct TAT inverse, and then, well, T inverse is the same as T, right? So they're just the same matrix. Multiply this big matrix on the left and the right. Well, what happens when we do that? Well, first we'll multiply this matrix here, these two together, right, to get this term here. Then we multiply on the left here by this other matrix, and we get the set of dynamics given here. And this actually corresponds to x dot e dot equals blank x e. Yep. So now we see that the eigenvalues of this matrix are equivalent to the eigenvalues of this matrix. But the eigenvalues of this matrix are actually just easy to tell what they are, right? Because it has this important lower 0 here. And so what we know is that the eigenvalues of this upper triangular matrix are just the eigenvalues of the diagonal elements of that matrix, right? So we know then that we've established then that if we control the eigenvalues of a plus ac and we control the eigenvalues of a plus bk, our closed loop system, our observer-based controller, will have the eigenvalues that we dictated through the choice of L and K. Okay. Finally, right, we can, if we want to do more LMIs, right, we can stack them up, right? We can do D-stability for our observer as well. So if we want our closed loop observer-based controller to now have a specific range of eigenvalues, say given by those LMI regions that we talked about in the previous lecture, right? Well, that was lecture 4. we can apply the results of Duality and Gahine and get an LMI for d-stability of the observer as well. And that'll, if we couple that with an LMI for the controller, that'll guarantee that all of the eigenvalues of our closed loop system will lie in our desired LMI region. Right? So if we add d-stability for the controller, then we get d-stability for the closed loops observer-based controller. Right. And of course, remember where these came from. This was the one for TR. This one's the one for settling time. And this one was the one for percent overshoot. So feedback control, we can assign our eigenvalues, we can put them in regions of the complex plane and do all sorts of lovely things. Okay, so now I'm going to break again, and this concludes our discussion of observability and controllability for continuous time. Very briefly in the last 3 slides, I'm going to cover the discrete time case, and I'll add a summary here at the end, very briefly in the remaining 3 slides. All right, so at that point, I'll stop and we can take a break, and we'll come back, and I hope it shouldn't last more than 5 or 10 minutes.